Welcome. In this lecture, I'm going to give some of the kind of typical terminology that we use when we talk about functions. So we're just going to start out with, so suppose. And we still have that S and T are sets, so S and T. So these are sets. And then we have that we have our function f that goes from S to T, so f from S to T, so S to T is a function. I actually meant to do it in blue, so it is a function. Okay, so this is going to be true throughout. So we say that in this particular circumstance, we say that S is the domain of S, so of F. Okay, so let's just get started on the terminology. Okay, so S is called the domain of F, so S is the domain of F. Okay. And then we have that T is called the codomain. Of this function F. Okay, so the picture just starting with these two is that we have, here's my S, which is my domain, and the function F is going to take everything in there. So F is my function that's going to take everything into the codomain. Okay. But now we need some more specific language because it's possible that we don't actually hit everything in the codomain. Like not everything, like each element of S has to get mapped into the codomain, but there might be elements of the codomain that nothing goes to. Okay, so we need a little bit of different terminology for that. So definition. So the image I have fewer colors than I'd like to have. So the image okay, which is also called the range, so also called the range. It's just another name for it, of F. Of F is going to be, so this is a particular set and it has some notation for it. So we write it like this. So you write it as F of, then you put your entire set in here. So this is going to equal by definition. So then by definition, this is equal to the notation for it, and this is equal to, this means by definition this is equal to the set of all. So I'm going to apply F to each element S that is in my set. So the set, such that, right, so I'm taking all of the images of all of the points in S, okay, or all the elements of S. Okay, and then it's important to kind of realize that this sits inside of the codomain. Here it's hidden. Okay, so now we can add to this picture that my range is sitting inside of here. So here is the range sitting inside of my codomain, like this. Okay, and then, so what actually happens with this function is it doesn't just go into here. We can actually like adjust this now. It actually maps everything goes into here. So we kind of like gave extra room. It's kind of like having a function where the outputs are always positive, but you still say that the codomains are real numbers. You still say, like, for example, when you talk about the function f of x equals x squared, you usually say it goes from the real numbers to the real numbers, and the real numbers are the codomain. But really, you're never going to get an output of a negative number. So you really mean the non-negative real numbers. And so that would be what the image or range would be. Okay? And then there's one other definition that I want. So the other definition that I want is that suppose that we have, so suppose we're going to reuse colors. So over there, so forget about our, forget that we, you know, some of our color scheme there. And we're going to have this subset. Actually, so suppose x is a subset of t. I know I've been using it for a function, but now it's not going to be. It's going to be a subset of t. Okay, so x is a set that lives inside of our t, which was our codomain. Right, this is my codomain t. And then my range, right, this range is my f of all of s. Okay, so I have this set in here, so I might want to talk about the pre-image of this. Okay, so I'm using again orange. Please don't get confused by that. I just don't have any more colors. So definition. The pre-image of x so of this set x, it's sitting inside of there. Okay, so the pre-image of x is going to be the set of all. So we have the set of all. So the pre-image is going to live inside of the domain. So this is going to be the set of all s in s such that, so the pre-image, once again, I want to give this the, okay, so there's notation for this. So the notation for this is f inverse of x. Notice that this is like the inverse of a set. So this does not mean that I'm applying the inverse function. It's just notation to mean, because how would I be applying this to the set? So this is just, I don't even know that my function has an inverse. I'm just going to give a definition, and this is the notation. And I know that's confusing. You would not be the first student in the history of the universe to get confused by that. In fact, let me just kind of write a little note here. This doesn't mean the inverse function. F may not even have a function inverse. Okay, so that's kind of an important note because this has caused so many students to get so confused. Okay, so what is this? So this is equal to the set of all. So this is going to be elements in S satisfying that when I apply F to that element, I know I've double used blue here. Hope that's not too confusing. So when I apply F to that element, that I end up inside of this set X. Okay, so this ends up being inside of the set X. Okay, and then I can close this up. So So this is a set. Notice that this set actually lives inside of S, right? Because the elements are elements of S. So this lives inside of S. Okay. So i.e. So i.e. this is a subset of S. So this is a subset of S consisting precisely of all elements of S. So consisting precisely of all elements of S Okay, so elements of S, so these are of all elements of S mapped by F, so mapped by F, right, to an element of X, so to an element of X. Okay, so we're looking at all elements in S that are mapped by F to into that subset X. So let's just kind of draw our picture here. So I have S, I have T, I have this X that's living inside of here, right? It's some subset living inside of here. Okay, and then I'm going to look at everything, and you know, maybe I have a piece over here, maybe I have a piece over here, maybe I have a piece over here. Okay, I'm just looking at these things that go into X. Like the F is going to map them into X. Nothing else can go into X. So anything on the outside has to go to somewhere else in T. I'm just interested precisely in the ones that go into X. Okay? So, this is just a lot of new terminology. You gotta get used to it. I know it's actually, this is, in my experience in teaching, one of the things that I found in advanced mathematics is that one of the things that catches students up the most is staying on top of the terminology. And they think they're getting confused by deeper things and all these things, and it's really, you just have to, like, learn the terminology as you go along. Otherwise, you don't understand the next thing being explained because it's being explained in the terminology you didn't know yet. So it's worthwhile to get yourself comfortable with the terminology, like each lecture, you know, practice it, memorize it, and then move on to the next thing. Otherwise, it's gonna build up to where it's too difficult. Okay, so just to kind of go through it, when you have a function that's gonna go, right, so you have the domain. It goes from the domain to the codomain, but the codomain may have extra stuff that isn't the image of anything. Kind of like if I always had f of x equals x squared, I don't hit everything in the real numbers. So there's like extra stuff there. And if I just want to restrict to the stuff that actually is in the image, then it's the image or the range. Okay? And then the other terminology, and this one students do find this tricky, is the preimage. This is not the function inverse. What I'm doing is I'm looking at everything that will get mapped into that set X. Okay? And so you kind of have to think of it like that. Okay, so I hope that's helpful and made some sense. And practice, and I will see you in the next lecture.